So now we talk about Krull's principal ideal theorem. So Krull's principal ideal theorem says that, so you start with R, which is a Noetherian ring, and you pick up an element A in this Noetherian ring R. Then the height of the minimal prime ideal P of A is at most 1. So what it means is, more concretely, if you consider a chain of prime ideals like this, Q prime is contained within Q, which is strictly contained within P, so there is no equality here in R. So this height of this prime ideal P, which is a minimal prime ideal containing A, is at most 1. So that means that these two have to be equal, because this P strictly contains Q, so there has to be an equality here because the height is at most 1. So we have to show that Q is equal to Q prime. So these two are equal, so the height is 1. So our strategy is this: you start with this ring R and then you modulo out with Q prime. So you have this ring A, which is R modulo Q prime, and we have this one-to-one correspondence here. So prime ideals in R modulo Q prime are precisely prime ideals of the ring R which contain Q prime. So this P is containing Q prime, so we have this P contains Q prime, so this P will become a prime ideal here. So but its form here is P modulo Q prime. So we have this ideal P prime which is set as P modulo Q prime. Now we can localize at this prime ideal P prime, which we are saying is this. So you can localize, you get this local ring A P prime, and in this local ring, so now you have this local ring AP prime. So what are the prime ideals in AP prime? They are precisely the prime ideals of A contained in P prime. So this Q is also contained in P here, so Q is contained within P here. So and we have a Q prime right here, so we can talk about Q modulo Q prime here, which we say is B. So obviously B is also contained within our P prime. So this B is an ideal in ring AP prime. So this B is an ideal in ring AP prime, and we are going to say that this because this B has come from here, prime ideals of A contained within P prime. In P prime you have this prime ideal Q modulo Q prime. So P prime contains this ideal B, so this ideal B, and there is one-to-one correspondence here also, so this becomes B here. So what we are going to do is we are going to show that this ideal B is actually 0. So that is Q modulo Q prime is 0. That will make Q equals to Q prime. So this is in the ring AP prime, and therefore all the result carries over to R, because of these two relations. So this B is 0 would make Q equals to Q prime. Now we are going to do is that abuse the notation, this, because we are going to be working in this ring, so we are essentially going to be working in this ring and showing that this ideal B is 0 in this ring. So this is what we are going to show. Now we will abuse the notation because it's not going to make much of a difference. AP prime we will set as R, and this B we will set as Q. So we are just forgetting about modulo by Q prime and then localizing it. So we are just going to rename this. So this is just abuse of notation. So we are not forgetting anything. I mean, we just rewriting it like this because we will have to localize a couple of times again. So this we have to remember, but it does not make any difference, because if R is Noetherian, then its localization is also Noetherian. So we will prove these two results, that symbolic power of Q is contained with the symbolic power of Q to the n plus 1 plus A, and this A is coming from here, and symbolic power of Q to the n is equal to Q to the n plus 1 plus P times Q symbolic power of nth symbolic power of Q, and this P is this precisely prime ideal. So given this 2, we can prove our theorem, and then we will prove this 1 and 2. So we start by quotienting this out. So we will quotient it by qn plus 1. So quotient it by qn plus 1, so this will go away. You will have q symbolic power, nth symbolic power of q modulo this symbolic power here, and then you have this modulo this. So now you can use Nakayama lemma. You see this thing is same as this thing right here, so you have this equal to 0. So that follows from Nakayama's lemma. So this 0 means that both of them are equal. Now you can localize, so you localize with respect to this ideal q. Now notice again, this r is actually this a p prime and this q is actually b, but we are just mechanically following from here. We just modulo out, use Nakayama lemma, this becomes equal, localize. Now in the lecture on symbolic powers, in that lemma we showed that this is equal to this. So nth symbolic power of ideal q is same as the nth symbolic power of q if you localize in this ring RQ, if you're talking about this localized ring, and this is also equal. So if these two are equal, this equality carries over here. So this side you can rewrite as is QRQ times QN RQ. So now again you use Nakayama lemma, this is same as this. So we have to have the case that Q and RQ is 0 by Nakayama lemma, but R is an integral domain, so therefore it has to be the case that Q is 0, and that's what we wanted to show. So we had a set, we wanted to show this equal to 0 because we had set Q as a B. So essentially we have shown that B is 0 and Q is equal to Q prime. So now only thing we have to show is 1 and 2. So first we will show 1 because it is used in the proof of 2. So now we will prove this 1. So first again notice that we are working in this ring R, which is a p prime. Now once you localize the ring, this localized ring also has a maximal ideal, and the maximal ideal of this ring is precisely this p prime a p prime. So this is the maximal ideal of our ring here, and this is a unique maximal ideal because localization means you actually make a ring local. So this is the unique maximal ideal. So as we said before, we started with this ring R and we ended up at a p prime, but localization of Noetherian ring gives you Noetherian ring, so this is Noetherian. So if you have R modulo a, so this is Noetherian, where R means that it is this thing. And now notice that it has dimension 0. So dimension 0 precisely because every ideal of this ring is of the form p modulo a. So now we are working with this ring, so instead of p we are actually thinking of p prime, and this ideal is actually the maximal ideal. This is the maximal ideal. So this is a maximal ideal, but we are given that each such ideal is minimal over a. So you have a maximal ideal which is also minimal, so therefore dimension is 0. So Noetherian ring with dimension 0 if and only if it is Artinian. So now our this ring R becomes Artinian. This R modulo a, this becomes an Artinian ring. So this is an Artinian ring. So now you can consider the following chain. So you have this following chain, you have symbolic powers here. So this following chain will stabilize after a certain number of steps. So after some n it will stabilize. So you will have equality in the so denominator is always the same, so you will have equality in the numerator. So nth symbolic power of ideal q plus a is equal to n plus 1 symbolic power of q plus this a, and which would imply that this q to the nth symbolic power, this is contained within something like this, and this is what we wanted to show. So I mean you could show other things from here also, but we are just using this particular result so that we can, so you can have inclusion in the opposite direction, but we need this form to be used in 2. So this is what we wanted to show in 1. So now we can prove 2. So now we want to prove this 2. So this inclusion is obvious because by definition this n plus 1 symbolic power of q is contained within the nth symbolic power of q, and this q nth symbolic power of q here is obviously contained within here even after multiplication here. So this is obvious. We have to show the other side, so we want to show this inclusion. So what we are going to do is we are going to start with x lying here in the nth symbolic power of ideal q, and then we will show that this x will eventually lie in the right hand side. So you will start with x in here and then we'll show x lies in here, so that will prove this inclusion. So from 1 above, if x is of this form, then you can write it in some form like this. So you can write it as c plus ar, where c is in n plus 1 symbolic power of q and r is in r. So we want to go from here to here. So c we have already taken here. So what we have to show that this ar now is in p times q to the symbolic power of n. So this is what we want to show. So now r lies in ring R because this is an ideal generated by A. So you have this. So now you say AR is equal to x minus c, and this lies in the nth symbolic power of q, again precisely because this c lies within n plus 1 symbolic power of q, which in turn lies within here. So c lies here, and x is anyway lying in the nth symbolic power of q. So x minus c lies in here. So AR lies in here, and this Qn is q primary. Now notice that A does not lie in q. So this is precisely because this ideal P is minimal over A. So this P prime ideal is minimal over A. So if A would lie in Q, and this is a chain of prime ideals, then P is no longer minimal over A. So you have to have the case that A does not lie in Q. So notice again, this Q is essentially here is B, which again is Q modulo Q prime, but the same story holds. So A does not lie within Q. So but Qn is Q primary. So if A does not lie within Q, then the other element, because AR lies in the nth symbolic power of Qn, where Qn is Q primary. So by definition, if A does not lie in Q, then R has to lie in this Qn, and that was the story. So if R lies in Qn, then AR would also lie in PQn, precisely because A lies within P. So this is the height of minimal prime ideal of A. So A obviously is contained within P. So A lies within P, R lies within Qn, and that's what we wanted to show.